Okay. All right. Hello, everyone. My name is Chris Ellis. I'm a member of SecLab at the Ohio State University. I'm very happy to be back this year at PETS to be able to present some of my recent research on exclusive use systems. This work was done with my advisor, Dr. Zhiqiang. So I've defined in previous work exclusive use basically being the relationship between trusted entities. So what's interesting is when you look at these communication patterns and how they differ from non-trusted entities, we can actually reveal quite a bit of information here. So a lot of these systems will actually have a lot of binary signals that may seem a bit benign at first, but what we find is that there actually pose a risk to user privacy. So when we observe these signals, we can see that there's actually quite a bit of semantics there. This is going to enable behavioral inference or wide native inference, and which can also support user re-identification. Fortunately, it's not all doom and gloom because we can measure this anonymity, pre and post countermeasure deployment, and enhance privacy for users. So main contributions here of my work today, formalization of this exclusive use leakage where we model these binary observables, quantification framework where we have complementary methods to measure anonymity loss, as well as a threat taxonomy around 3 dimensions. And then we wrap it up with a case study evaluation on Microsoft Teams. So, quick look at the formalization here. So we're looking at the scenario basically where there's a one-to-one mapping between users and resources. So that's basically captured here. But then for each user at a discrete time step t, we can look at a raw feature space and then throw this into a digitization function for each one of those features that basically outputs 0 or 1, or kind of like hot dog, no hot dog. But then a singular digitized observation is basically a binary vector here of all those functions. For some user at a TMT, and as you can imagine, then we can do a sequence of those. So then we can throw that into to extracting the features. Is this working? To extract more features right here, and then we have a reference vector, and then we can calculate the Euclidean distance. We have a tuning parameter, come up with our likelihood. So we can then normalize and calculate our posterior with uniform prior. It's very exciting. So for actual quantification, then we have our construction using Shannon entropy. Don't be intimidated by this. It's basically the previous formulation applied to Shannon entropy there with our likelihood function. But then we can actually, this allows us to measure the privacy loss in bits. So at the top there, we have a baseline for log 2 of n, and then L capturing our delta between the uniform baseline or previous prior baseline and then our observed Shannon entropy. We also measure and report on base vulnerability, which is basically attacker confidence. And then we also do an indistinguishability game between pairwise users. So there's a quick example here. So say we have uniform priors across 4 users. So this is 0.25. Then we calculate these posteriors. So we have these values here. So we have our baseline anonymity here of 2 bits from Shannon entropy. And then we can calculate that to be 1.32 bits approximately. And then we can look at our max posterior there and find that attacker confidence is approximately 70%. And then an entropy loss of 0.68 bits. Down from 2. I'm sorry, the delta between that. So I've also introduced a threat taxonomy across 3 dimensions here. So for attacker capability, which goes down in the leaves there, but we have observation time, access level, locale, and scope, passive and active observation methods, as well as a variety of inference between users, relationships, and behaviors. So this helps us characterize once we find threats that we can socialize and share with the community or other system defenders. So all this research actually first started when I was doing some traffic analysis on Microsoft Teams. And I noticed some patterns for specific events here. So on the top right, you can see that there's this fixed sequence here of 184 bytes followed by 250. And this is effectively that presence indicator that if you've gone inactive and then you then this is the presence indicator that's out there. Following that is typing. So this is a tuple here. That first number we can call kind of like a context or message ID. So there it's 2937, followed by the fixed bytes 205 and 89. You can see if you took a quick break and started typing again, you'd see the same sequence. Once the user has actually sent the message, you see that same, we'll call it the message ID again, 2937, followed by some number of bytes, that is the message sent indicator. If the user were to start typing again, that context changes. So now that we have our encrypted traffic, we have our pattern matches, we can throw this in and create a binary signal vector, which I explained earlier. This is then going to allow the adversarial inference. So what we did here is actually simulate Microsoft Teams traffic across 4 behavioral profiles: deliberative, low engagement, high frequency, and intermittent. This was all informed by message platform analytics, as well as Dolly Parton's hit song 9 to 5, It's a Reasonable Working Day. Um, so we have our presence, typing, and message send indicators, as you can see across all these profiles. We have 16 users for our anonymity set. For each one of those, we did 10 runs, dropping them into max in certain evaluations. So jumping back to our threat taxonomy now, though, what we can see here is for attacker capability, we can see this is longitudinal over time, unprivileged, global, and mono system. And then a passive sniffing observation method, which then allows us to look at our encrypted traffic for packet sizes and timings as well for feature extraction, to be able to do our pattern matching, binary signal vector, posterior update, which then is going to allow identity resolution, presence, session attributes, and behavior inference. So here's our pairwise indistinguishability game. Just for time, I'll just kind of do a summary here, but if you look at the first pair, A versus B, you can see a posterior probability of 0.85 and an anonymity loss of 0.42 bits. We also do this treatment here pairwise on all 16 users as well. So I want to point out that baseline there of 0.25, which is effectively a coin toss there. But we can see for the absolute majority of these profiles that they're far exceeding that. But then looking more to the real world, we've got our pool evaluation. So this is where we're considering all 16 users. We're looking at posterior probabilities as well as anonymity loss here as well. So that dotted line on the bottom, again, is our baseline. Again, random guess, anonymity of 1 over 16 or 6.25%. So if you look at users, this is an average of the profiles for A and C. We can see a vulnerability range from an average of 0.19 to 0.29, as well as an anonymity loss in bits from approximately 0.78 to 1. More interestingly, say D2, a little bit more of an outlier, so we have 0.71 confidence, attacker confidence, and then an anonymity loss of 2.44 bits. Again, in a more real-world application now, here we can do true rank re-identification. So this is actually all 160 runs. So in the top one, accuracy, we have 54.7%, which is effectively saying that if we have one shot, we are actually re-identifying over half of these users on just one guess. If we've got 3 guesses, we're going up all the way up to 89.1%. So we've got a median 2.23 and the median true rank of 1. So quick chat here. So we're just doing this case study, right? But this can actually help you, as I mentioned, evaluate defenses pre and post. This is about applicability for VPNs, APIs, and all the smarts out there. I think as others have presented, there's obviously additional information on proper models. We can also do cross-system correlation. We can have greater inference power. And I think very importantly, I'd like to talk about this in terms of the inherent flaw in network communication. I think it's very important work that we're doing in this area, because what this is basically doing is imposing consent, right, on its users. There's no meaningful way to opt out. Right, this is network traffic. So I think this is a calling to researchers to make sure that we can protect users worldwide. A couple of future work here. I think it'd be wonderful to have actually scoring metrics like similar to CVSS for privacy. And with that, thank you very much. Happy to check out the post here for anything else. Thank you again to all the PITS organizers as well.